Hey guys, my name's Thatcher and welcome to episode 9 of my DCTL coding tutorial series. This is going to be the last episode and we're going to be covering various debugging and coding tricks that I recommend in order to improve your overall workflow and improve your ability to share your DCTLs. So one thing that I see a lot of people do when they just start out writing DCTLs, especially if DCTL is more or less their first coding language, is that they don't really have any code style, and then when you read their DCTLs, it's very difficult to follow the logic of their code. This can be improved pretty substantially if you use a code formatter. On Mac OS, there's a tool called clang-format, which I've written right here, clang-format. And it also works as a Visual Studio Code plugin so that once you have it set up, you can just run code formatting on your DCTLs. In order to use clang-format, you do need to set up a configuration file called .clang-format in one of your parent directories. In this case, I have it in the directory holding all of my different lesson files and DCTLs. And you can just copy this one from my GitHub. I have a link for that in the description below. These are my preferred options for clang-format. If you don't have this file, it will just use the default clang-format settings, which are visually less appealing in my opinion. One that I do want to highlight here is the column limit. You do want to set this number to be greater than the length of the typical transform function. So I think 140 is usually a good value for that. All right, so let's go ahead and take this intentionally poorly formatted DCTL and run our code formatting. So I'm going to do Command-Shift-P and type format document. And then we'll see that all of my indentation has been fixed. My curly braces have been placed on the same line as my control flow and functions. However, there is one problem, which is that define UI params, these have to be declared on a single line. Otherwise, Resolve doesn't actually do the right thing with them. So in order to make clang-format skip the parameter sections of my DCTLs, I have to use a secret comment here. So I'm going to undo my clang formatting, and I'm going to add a set of comments before and after my UI parameters. The first one is going to be clang format off. The second one is going to be clang format on. I do think you need a space here between the slashes and clang format in order for it to work, but I don't fully recall. I'm going to go ahead and save that and then run format document again, and we can see that our code looks a lot better now. Okay, so now that we've made our DCTL pretty to read, I do want to actually walk through some of the logic of this DCTL. So this one I've titled it Problems, and then I have another one titled Solutions that has all the problems fixed. Let's hop into Fusion and see how this DCTL performs. I'm going to start off with this image that's a linear ramp from -1 to +1. And I have my Solutions DCTL pulled up. And we can see what we wanted to do. So when the combo box value is set to raise to a power, we're simply going to raise the input code value to some power. And then when the dropdown says just return a half, we're just going to return 0.5. If we load up our problems DCTL, we see instead that the power slider doesn't make any difference. That's because this DCTL failed to compile. If we pull up the logs, we see this interesting error message. It says transform DCTL function has wrong number of arguments. There are only 0 arguments of the required 7 arguments. Here's what's going on. In DaVinci Resolve, when the software parses your DCTL, it's going to be doing some string matching in order to find your transform function. Once it's done that, it's going to add more parameters under the hood, like power and this is my combo box variable, that will be added to the arguments list for transform. However, their string matching is not very sophisticated and isn't smart enough to avoid comments. As a result, this comment here is detected incorrectly as the transform function. What I recommend is to never have the word transform in all lowercase within a comment. So I'm going to go ahead and change this to transform with an uppercase T so that it doesn't get detected. Let's go ahead and save this and open it back up in Resolve. Hit reload, and we see that it still does not compile. Opening up the terminal, we now have new error messages. It says invalid DCTL format, no return value. This certainly confused me the first time I saw it because we do have a return statement in our transform function. However, once again, Resolve has made a mistake. When reading your transform function, they're also doing a string matching check to make sure that your transform function has a return statement. Unfortunately, they're just doing a string match to find the word return anywhere within the body of the transform function. In this case, I have the word return within a comment, and that's going to be problematic for Resolve. So what I recommend is to simply, in this case, modify the comment so that it doesn't include the word return in all lowercase. Let's save this and open it up in Resolve. All right, so we see that the DCTL now compiles. Unfortunately, we're not done yet. This DCTL is actually going to fail on NVIDIA systems. Let's open up this DCTL on my Windows computer and see what happens. All right, so here we are in Windows, and we can see that the DCTL has unfortunately failed to compile. If we open up our logs, we can see the problem. We get this incredibly cryptic message here that says, error, expected an expression. Now, this is a remarkably frustrating error to debug because it doesn't really tell us where in the code it happened. It doesn't show us the adjacent lines where the problem took place. Let me show you a trick to figure out what line number this error takes place on. You'll notice that it specifies line 3100, which is obviously enormous. Our DCTL only has 20 lines. However, it turns out that this line 3100 is simply offset from the line number that's within your DCTL. Here's the trick. At the very top of my DCTL, I'm going to add the line #warning, and I'm just going to say line 1. This is a preprocessor instruction so that when the compiler runs, it will print out the word line 1 as a warning. Let's copy our DCTL over and then hit reload. Obviously, it still doesn't compile because we haven't fixed any problems. But when we go into our error logs and make sure it's refreshed, we can see here, there's a warning, line 1, and then we get our old expected an expression error. However, we can now see that line 1 corresponds to errors on line 3087. That means that this line number shown in the logs is simply the line number in our text file plus 3086. As a result, I can take 3101 and subtract 3086, and that'll give me the line number that this error takes place on. The difference, if I'm doing my math correctly, I believe is 15. So we should expect to see this error correspond to a problem on line 15. In our DCTL, we see that line 15 here is this line. Hey guys, it's Editor Thatcher here. So I do want to say that this approach that we use with #warning line 1 does in fact work. I've used it a lot, but in the last week, since I actually recorded that video, I did find a better approach that we can use in order to find the right line numbers in your error messages. What we're going to do instead of doing #warning is we're going to instead use a different preprocessor instruction called #line. After #line, we indicate a number, which is going to be the line number of the following line. So that's why it's 2. It's because this next line is going to be line 2. And optionally, one other thing you can do is also indicate the file name. You don't have to do this, but as a third argument in double quotation marks here, we're going to say DCTL tutorial 9 problems.dctl. So I've indicated the file name so that when I get the error message, it will tell me exactly what file the error took place in. So let's go ahead and save this and paste it in and see how the error message looks instead now. Hit reload over here. And now we see DaVinci CTL compilation failed. It's nice enough to say the new file name that we specified, DCTL tutorial 9 problems.dctl. In line 15, we got this error, expected an expression. This is a huge improvement over the warning thing because this line number here, 15, is now actually just the correct line number that the error took place on. You don't have to do any math in your head. So for the rest of the video, it's going to say #warning line 1 at the top here. But I do want you to be aware that this solution is far better, this #line, and then you just do #line 2. You don't need to have this string. I do strongly recommend that you put this sort of thing after any include statements. And if you want to debug your header files, you would put this at the top of each header file. But that being said, keep that in mind and let's go back to the video. In our DCTL, we see that line 15 here is this line. We got the error expected an expression on this assignment to output. What's going on is that on NVIDIA systems, but not on macOS, you can make an assignment using the curly braces only on the line in which a variable is declared. So here I've declared output as a float 3 and set it equal to these 3 values wrapped in curly braces. I could do that on this line, but I am not allowed to do that on any other line. On this line, I instead need to use the function makeFloat3. This is true for float 3s on NVIDIA systems, as well as structs and arrays. Make sure that when you use the curly braces to assign an initial value to something, you only do it on lines in which the variable was declared, as in you establish the type of that variable. I'm not even allowed to do this. This would result in a similar expected and expression error on an NVIDIA system. All right, let's see if our DCTL compiles now. Okay, it looks like the DCTL works. If you remember what we had on the macOS side just moments ago, when the power was set equal to 2, we had a U shape in the waveform. On this NVIDIA system, we have the power set to 2. However, on the left-hand side, we can see in the lower left-hand corner that all 3 channels are set to nan, or not a number. As it turns out, these pixels correspond to when the input code value is negative. So what's going on here is that powf, when the first argument, the base, is negative, the behavior is undefined. On macOS, they're nice enough that when the power is an integer and the base is negative, they still have a defined output. However, on NVIDIA systems, when the first argument to powf is negative, it always returns not a number. It is my belief that in your DCTLs, you should try to have the same behavior on all systems. Even if you're happy with the macOS behavior, you would want powf to do the same thing on an NVIDIA system too. Let's get some inspiration from the color space transform as to how this might behave. Let's set the power equal to 2.4 in our DCTL, and in this color space transform, I have a transform from gamma 2.4 encoding to a linear encoding. This will actually raise the input code value to a power of 2.4. We can see that the right half perfectly matches the DCTL. However, the left half here continues in the negative direction, so that when the input is always increasing, like this, then the output here will also always be increasing. That is perhaps a creative decision made by Blackmagic. Alternatively, they could have simply said that for negative values, we should just return 0, or perhaps for negative values, we should reflect what we do on the positive side. However, for a color space transform, both of those options would make it difficult to recover these negative values later in an inverse transform. So let's go ahead and actually modify our powf calls so that we get this kind of behavior. So back in Visual Studio Code, let's define a new powf function. We're going to do device float. I'm just going to call it powf without the underscore. I like to use the underscore to indicate that it's one of the built-in functions, so I want my function to be different from those. We're simply going to give it a float base and a float exponent. In this function, we want it to behave the same way as powf, except when base is negative, we want it to be properly handled. We don't want to pass a negative number into the first argument of powf. I'm going to use a variation of powf that was told to me by a support engineer. But first, let's start off by just writing out the original statement. And we can go ahead and modify this appropriately. If we just wanted this graph to be symmetric, what we could do is we could take the absolute value of the base before we pass it into powf, using FABS, F absolute value. However, what we want instead is that when the base is negative, we return a negative output. The recommendation that Blackmagic gave me was to use copy sinf. What copy sinf does is it will take its first argument and make it negative if the second argument is negative. So we're going to pass in the base as the second argument so that when base is negative, we're going to take this positive number and make it negative. All right, let's use this new version of powf in place of underscore powf in these 3 places. I'm simply going to paste in powf in these 3 spots, save it, and let's open it back up in Resolve. Hitting reload, we do now see that the color space transform and the DCTL output the exact same values. Moving the power left and right, we can see that all of our pixel values are defined. All right, let's go back to macOS and talk about a few other things. So back in macOS here, one thing that I wanted to discuss was this note that's in the README, and you'll see this in a lot of DCTLs. This claim that note that float values must have an F character at the end, like 1.2F. And you'll notice that in all of my DCTLs, I've pretty much avoided putting in this F because it turns out that it's not really necessary. But it is worth discussing what that F actually means. So strictly speaking, in the C programming language, when you put an F after a constant, it tells the compiler to interpret this constant as a 32-bit floating point number. When you don't have the F, it tells the compiler to interpret this value as a 64-bit double precision floating point number, which is essentially just a float, but with more bits, so it can be more precise. In the vast majority of cases in a DCTL, this doesn't matter at all, because here we'll have 0.5 as a 64-bit floating point number, and it will be cast either by the arguments of makeFloat3 or perhaps the data type of the variable that will be storing this number into a 32-bit float. However, there are rare occasions where it would make a difference. As an example, suppose I were to write the following conditional. This expression will compare PR to 0.3333, which is a double. This implies that PR will be cast to a double, and because PR is a single precision float, it may actually differ from this value on the right, therefore always evaluating to false, even when it is as close as possible for a single precision float to this value. Instead, we could put the letter F here to force this to be a single precision float, and then compare these two numbers in a single precision float environment, in which case it is theoretically possible that PR could be equal to this number. That being said, I would strongly recommend that you never actually compare any floating point number in pure equality to any number other than like 0 or 1. 0 and 1 can both be perfectly represented by a float or a double, so the F wouldn't matter in that context. Truthfully, whenever you're comparing a float to some number, you do run into a risk of numerical precision problems resulting in that floating point number not being exactly what you thought it would be. So in general, comparisons between floats and some constant are risky, unless you use greater than or less than, or perhaps check that it is within some range of a target number. Here's another trick. For those of you who use GitHub to keep track of your code, you'll notice that in a lot of repositories, all the code just comes up as white, which is not very easy for someone to read if they're just browsing it in the web browser. In this case, this is a DCTL in Paul Doerr's DCTL repository, and you can see that there's no syntax highlighting within this DCTL. However, in the DCTLs in my repos, you'll see that we do have some useful syntax highlighting with types and control statements and whatnot that make it a lot more easy to read. The way that I set that up is by creating this .getAttributes file that simply has this one line in it, star.dctl linguist language equals C. I put that at the top of my repo, and you can find that in this .getAttributes file within the corresponding repo that's in the description below. What this does is it sets up C syntax highlighting for all files that end with .dctl. Another thing you might have noticed during this whole series is that within my LUT folder and inside my DCTL tutorial folder, I have this DCTL tutorial file, .dctl. You might have wondered, what's in this file? Why do I have it there? Well, if we take a look at this file, it's literally just a transform function and it just returns the current color. This DCTL does basically nothing. So then why do I have it? I have that DCTL tutorial file in that folder so that when I scroll through my DCTLs, there are these little dividers here. That makes it a lot easier for me to navigate my growing list of DCTLs. I just have a similar file at the top of each folder, and it starts with equal signs so that it always shows up first in alphabetical order. Here's another useful tip that will help you debug your DCTLs. A lot of DCTLs are in the same format as our DCTL from tutorial 3, this IDT, from flog2 to DaVinci Wide Gamut DaVinci Intermediate. Effectively, it takes in the input color, applies some operations to it, applies another operation, and applies yet one more operation before returning it. Sometimes, if not most of the time, you'll write a DCTL and it will compile, but there might be some kind of logic bug that can't be detected by the compiler. Unfortunately, DCTLs don't have print statements, so oftentimes it's difficult to figure out what each intermediate value was over this whole pipeline. One thing you can do to help yourself debug is to add early return statements during your transform function, so then you can inspect every single value that's within your code. For example, if I wanted to test my flog2 to linear function, I could simply write return out at this point, Then we can copy the DCTL over and open up Fusion. And inside Fusion, I can load up the DCTL with the early return statement and create a background that perhaps has some kind of known color that I need it to map to. In this case, 39%. I expect 39% to map to 18% gray. And there we have it. It corresponds to, well, 17.9, which is close enough. I believe that's accurate. This is useful in going through your code and making sure every single step outputs the correct value. The last tip I want to highlight is that sometimes you'll write a DCTL and it runs incredibly slowly. In my experience, there are usually two common suspects to this problem. The most common suspect is that you may have used text2d to retrieve the RGB colors of more than about 60, maybe 64 different pixels. Text2d is one of the slowest functions in a DCTL because it has to access a random pixel value from a fairly large block of memory. And that memory is often shared between many different parallel processes, so it can't be addressed very quickly. I would not recommend accessing the colors of more than 64 different pixels for a total of about 192 text2d calls. The other main reason your code might be slow would be that you're using an algorithm that has poor runtime complexity. If you want to look it up, there's a concept called big O notation, which represents an upper bound on how much more runtime an algorithm will take for an increasingly large input. To simplify, your code will typically consist of many different instructions that each take a small, constant amount of time, such as running powf or make float 3 or anything like that. So if you have for loops or while loops and you nest them within each other, you could quadratically or exponentially increase the amount of constant time operations that your DCTL needs to run in order to complete the transform function. So as an example, something that you might want to do when writing a DCTL is to make an algorithm that blurs the image. To blur an image, for the current pixel, you have to look up the pixels of a lot of its neighbors. Usually that would be neighbors within a square region of the frame. As your blur strength increases, the number of neighboring pixels that you'll have to look up the colors of will increase quadratically. It will increase quadratically because increasing blur strength requires you to look up more neighbors in the horizontal direction, as well as more neighbors in the vertical direction. The area of this rectangle increases quadratically with the side length. As a result, with DCTLs, it can become computationally expensive to blur an image with a large blur radius. So that pretty much concludes this last episode of the DCTL coding tutorial series. In this episode, we covered code formatting, these two words that you really want to avoid in comments being return and transform, assignment via curly braces being problematic on NVIDIA systems, and I recommend not doing it on any line other than where you declared a variable, how powf can be problematic when given a negative base, and how you can modify it to better suit your specific needs for a specific DCTL, identifying which line of code an error message took place on if the error message did not give you enough information to deduce it from that message alone, whether or not you really need to put f's after floating point constants, setting up syntax highlighting when viewing DCTLs in Github in your own repos, keeping your DCTLs organized with dummy DCTLs like this one DCTL tutorial with the equal signs around it, returning early within your transform function as a way to inspect a few different values, ideally within Fusion, and also how to avoid making slow code by using fast algorithms and avoiding making an excessive number of text2d calls. If you made it through this episode, as well as all the other ones, I appreciate you for sticking around, and please leave your thoughts or questions in the comments. Thanks everyone, and have a great day.